Okay, good morning everyone and welcome to the 2011 Royal Tyrrell Museum Speaker Series. Today, the Royal Tyrrell Museum and its cooperating society are proud to present Chris Capobianco. Chris is a fossil preparator here at the Royal Tyrrell Museum. Chris is originally from Mississauga in Ontario. He went to Carleton University in Ottawa to pursue an undergraduate degree in earth sciences with a concentration in vertebrate paleontology and paleoecology. After completing his degree, Chris came to the Royal Tyrrell Museum to work as a lab technician, a position he has occupied for the past year. While at Carleton University, Chris did an undergrad research project on a highly concentrated layer of fossil debris from Alberta. The goal of his research was to document that layer in order to better understand the history of sea level changes and the paleogeographic setting of the Western Interior Seaway 100 million years ago. It is the results of this study that Chris will present today in a talk entitled Bioclastic Conglomerates at the Albian-Cenomanian Boundary in the Western Interior Seaway, Composition and Stratigraphic Significance. And I didn't fumble over it, so that's good. So without further delay, I present you Mr. Chris Capobianco.
Thank you. So the most common question I've been getting over the past week since the title has come out has been, what does it mean? It's very long, and people I seem to be intimidated by it. So Francois got it correct. It's bioclastic conglomerates from the Albian-Cenomanian boundary in the Western Interior Sea, composition and stratigraphic significance. So I figured to start off, I would break down the title for you guys. So what is a bioclastic conglomerate? This essentially is a bioclastic conglomerate. You can see it's a dense accumulation of vertebrate material. There's generally very little in terms of siliciclastic or other types of sediment in there. It's mainly all bioclastic material, so invertebrate shells or vertebrate material like we have here. And so they're very important. They're associated with distinct gamma ray kicks on wireline logs. That's due to the high amount of phosphatic material, which is what bones mean. And they're also laterally correlative across the basin. And their significance is that they're good for sequence stratigraphic surface markers. Oh, but so the Albian-Cenomanian boundary, where is it? We have this nice international stratigraphic chart. And down here, we have the Cretaceous. And within the Cretaceous, here's the Albian-Cenomanian boundary. So it's listed at about 99.6. I've seen various numbers from 98.5 all the way down to 97.3 for the boundary. But it's important because it marks the boundary between the upper and the lower Cretaceous. Where are we? So the Western Interior Seaway, most people know, they see it as this one, or one that has going up into the Hudson Bay area. But to start off, in the early parts of the late early Cretaceous, the Western Interior Seaway really only stretched down from the Boreal Sea. It didn't really touch the Tethyan until later on when sea level rose. So we have the main areas all coming down from the Boreal Sea, coming down through, here's Alberta, right here, coming down into the southern United States. And then as sea level rose, it would come all the way down to the Tethyan Sea. But you can see from here, this one's from the late Albian at around 100 million years ago. And then the next paleogeographic map we have is from the late early Turonian, so 85 million years. So there's 15 million years in there that we don't really know what's happening, or no one really has the confidence to make a paleogeographic map. Here's the Maori Sea. That's what that area is called. And so the objectives of my study were to use previously described localities and well samples from Alberta to understand the composition and taphonomic character of the bioclastic layer. And this is marked by the fish scale marker bed right at the Albian-Cenomanian boundary. And then compare these localities to other extensively studied localities from the Manitoba Escarpment, which is on the eastern side of this Western Interior Seaway, And this will help address depositional history within the basin and gain insight into different depositional environments across the basin. So here's a more detailed stratigraphic framework for us. We have the Albian right here. We're going through a bit of a regressive cycle. We have the Westgate Formation marking the latest Albian. And then right here's that fish scale marker bed that I'm interested in, with this fish scale formation right above it. And so we can see that across the Southern Plains, Central Saskatchewan, and the Cold Lake area, we have this fish scale marker bed and the fish scales formation. So it's quite extensive and correlated. Here's a wireline log across the basin. So we start up in Cold Lake over here and then make our way down into southeastern Saskatchewan. And you can see the fish scales formation is seen right across the basin, and that those wireline kicks are all along this line. There's also another kick that's right about here at the base of the white specks formation, and that's another bioclastic conglomerate, but I didn't have time to put that into my study. So the materials I had one outcrop. It was an area in Judah, which is really close to Peace River. And then 3 core samples, one from the Paradise Well, which is in east central Saskatchewan, Alberta. And then the Cold Lake area had 2. We had the DDOB5 and the ROB5 core. And so my methods were to conduct a lithological analysis of the 3 cores, make polished thin sections of Judah and DDOB5, because those I had physical rock samples for, and then to analyze the vertebrate element types. This map is very blurry out here. But so here's the Judah sample up in northwestern Alberta, Paradise Well down here, and then this blown up section is the Cold Lake area, in which the 2 cores are quite nearby each other. Something to note is this is the extent of the fish scale marker bed, and it does not pass into the United States. In the United States, a similar layer goes by the Maori Formation. So it doesn't extend down that way, and it goes all the way over into Manitoba from the Yukon. So this is what a sample of my bioclastic conglomerate looks like. Obviously not the picturesque version I put in my other picture, but still, dense accumulation of vertebrate material, though it doesn't look like it. We have, it was very interesting because this sample, I mean, it's only 10 centimeters, so about the size of the palm of your hand. And we tried to break it down to further analyze some vertebrate material to use in the study, but started out with putting it into some acetic acid, about 8 to 10%, and didn't break down. There was not enough calcareous material in it. So we ended up putting it into a water bath and then putting that in an oven to help break it down, but nothing worked. So I was only able to use this for thin sectioning. Wasn't able to use it for any of the vertebrate analysis. And so previous work had been done on the Judah bone bed, which was the sample that I showed you. It was done by Leckie and others in 1992. And they didn't really know what was going on with the layer. It was described as an enigma. They had no idea. Well, they had sort of an idea what was going on, but they kind of seemed to be on opposite ends of the spectrum. They had one hypothesis saying that it was the peak of a marine transgression, so really high sea level, and that this would cause the undercurrent to winnow away the layer, leaving only fossil material left. But it also had many characteristics of a lag deposit, which is almost the complete opposite of that, showing very low sea level, which would cause the storm wave base to interact with the seafloor and winnow away some of the finer sediments. And so it can represent either a shallowing or the peak of a marine transgression. And so this is the work that I did. So I took the core, this one's from East Central Alberta, so the Paradise Well core, And it starts off analyzing from the middle of the Westgate Formation. And we had this shale layer, no fossils in it whatsoever. But it was abundant in foraminifera. There's all these different species of foraminifera, and they all die out right here at the boundary. There's no foraminifera above it. And here is the Bioclastic Conglomerate. It's actually a coarse sandstone in terms of size. And then we have some bentonites and where I found other fish material. But the densest accumulation was right here at the boundary, and then it fined as it went upwards. The Cold Lake area had another very similar one. Here are the samples that I took. Starts at about the same level. And same thing, shale layer goes up, Bioclastic Conglomerate, and then we have some fish remains found as we went up section, but they were very, very few and far between. Again, to note, the foraminifera do go extinct again at the boundary. There's this one that kind of peaked over, but it wasn't that much. The other core of the Cold Lake, this was Rob 5. The other one was DDOB5. And it started much shallower, so there's only one foraminiferous species able to be found. But same thing, we had the Bioclastic Conglomerate with fish scale or fish remains being found into the fish scale formation, but on a much less abundant scale. And that's demonstrated by right there. So for the thin sections, this is from the Judah bone bed. You can see there's an abundance of gypsum coming through the sample. That's what all this white stuff coming through it is. And when we looked at it closer, we have all these little kind of circle-looking things are actually silicate grains or quartz grains. And then we have phosphatic material, such as that and all these other brown-colored pieces. So looking at it up close, you can definitely see that it's a bioclastic conglomerate. The matrix here is a clay, but I didn't have time to do any direct analysis of it. The Cold Lake areas looks much different. There's still a lot of phosphatic material. It's all colored black here. But there's almost no siliciclastic material except this one round grain that I was able to find. It was all very, very rounded. And yeah, there seemed to be a common orientation kind of in this plane of the material, or at least the larger material. When I used the Paradise Well core material, I was able to distinguish 5 elemental types. Those fossils that I had were very fragmented, and it was very difficult to identify a lot of them. But these are the very picturesque or pretty ones. A lot of them didn't look like that. But we had limb supports. That's just what I labeled them as. Teeth. CF pycnodont, which is a type of fossil. This is part of the skull, I believe. It had a very a bumpy surface that Steve was able to identify. Vertebrae, and then fish scales. The fish scales were by far the largest fragments that I found compared to the other ones. The scale bar is on a 1 millimeter basis, so everything was very small. It was all under a microscope. And so I was able to put it into a graph and see what the abundances were. So I found 180 fragments that I used, and there's very little pycnodont because that's very, very specific. But vertebrae were also very, very difficult to find. Teeth were by far the most abundant, with scales also being abundant. But they were on ones that were large, were easy to identify. Smaller fragments were also easy to identify because they had almost a fingerprint texture to them. So they were able to distinguish them, but they could have been fragments of other ones and making the number a lot higher. And then fin supports were found in quite a large abundance. So taking all of this information, I put it into this table to look at what this could infer for paleogeography. And so the Judah bone bed had this random orientation with very angular pieces. The sorting was moderate. There still was a large range of different sizes. But there was quite a bit of siliciclastic material. The phosphatic component was obviously abundant because it's part of a bone bed, or bioclastic conglomerate, so that would be the most abundant fragment in there. And so I interpreted it as a lag deposit. So what happened was sea level was really low, and this allowed the wave base to interact with the seafloor, take away all the finer material, and leave just the coarser material, which happened to be this phosphatic material. Paradise Well was a bit different. It had random orientation again, angular and fragmented pieces. That was all the fragments that I just showed you. And so the sorting here was very poor. We had a wide range of sediment sizes, and there was very rare, like very few siliciclastic components. I didn't find any when I sorted out the vertebrate material, but you could see some. And then in the phosphatic department, it was abundant. So I interpreted it as a tempestite. And what a tempestite is it's a storm deposit. So you can see that it was randomly oriented, angular and fragmented pieces, poor sorting. So it was an event that happened very fast and deposited this layer. The Cold Lake area was on a bit of a different end of the spectrum. It had kind of a uniform orientation. It seemed to be in this one direction, and very rounded fragments, especially in the phosphatic department. Therefore, it was well sorted. There was few siliciclastic components found, like that one round grain. And so here there must have been some sort of current or unidirectional flow that would distinguish it, that made it distinguishable. And so we have three different types of depositional environments. And so I compared this to the Manitoba escarpment, which has been very well studied by Steve Kumba and others. And goes from east central Saskatchewan down into right through Manitoba into North Dakota, but it's a series of these kind of upland hills which have many bioclastic conglomerates in it. This is also from later on in the Cenomanian. It's early middle Cenomanian, I believe. So it's a little bit further in, but again, it's a bioclastic conglomerate that I can compare it to. And this was the locality specifically that I used. And yes, all these are oyster shells. So when I compared the element types, I found that there's a much higher abundance of teeth than in Aaron Phillips' work, but he had a much greater amount of fish bones. He also had a larger data set. His was for a master's. Mine was an undergraduate thesis. But I sort of thought that because there is a higher abundance of teeth, could possibly be a more powerful storm that would have deposited this layer, because this is from the Paradise Well core. And similar elements indicated a similar paleo environment to me, and he indicated it as distant to the paleo shoreline, and that's kind of what I went with as well. So I'd also like to add that where my localities were in Alberta, they seem to be in the central part of the Western Canadian sedimentary basin. And so it'd be a much deeper area anyways, but because of what I've interpreted, sea level must have been really low during this time, making it a much narrower seaway, or at least isolated pockets in the seaway. So the localities from the central region of the Western Interior Seaway show a distinct bioclastic layer that has been associated with well-documented global sea level change, sea level low stand at the Albian-Cenomanian boundary. All the benthic foraminifera present disappeared, and the overlying fish scales formation is rich in organic matter and phosphatic debris. Therefore, as sea level dropped, the Western Interior Seaway became a shallow basin where waves and currents reworked the seafloor, concentrating phosphatic debris, particular in parts that are siliciclastically starved. And as sea level rose, fine sediments started to deposit again, slowly diluting the phosphatic component in the sediment. So that's part of why there was demonstrating that. And then sedimentation rates were low during the deposition of the fish scales formation, and it's interpreted as a condensed section. So that's my talk and what I did. I'd like to thank Claudia, she was my supervisor, and Steve and Rick Day from the Canadian Museum of Nature helped me try and break down my specimen, so that was a lot on him. Peter Jones made thin sections for me, or he did the geochemical analysis, and obviously the Department of Earth Sciences and Francois for letting me present my material. So that's it.